Hey guys, so in this video we're going to talk about the center of mass and how it can be useful. So on the screen we have a massless rod or a beam, but there are 2 point masses located at each end of the rod. The 2 point masses are painted in blue. The beam rests on a flat surface, on a table, and you can imagine that we begin to push the beam so that eventually one end of it goes over the edge, and at a certain point the beam will fall over, it will tip over. For example, if the right end of the beam is just over the edge, then we can imagine that this is probably not going to fall over, it's not going to fall down. So we want to basically answer the question of what is the maximum distance that the beam can pass over the edge. If we draw in gray the distance between the table, the vertical line, and the right edge of the beam, then what will be the maximum length of this gray line before the beam falls over? Now, even though we haven't really discussed rigid bodies, we can still solve this problem more easily by talking about its center of mass. In a simple body like this rod or this beam, where we assume that both point masses are the same mass and the same shape, they're both infinitely small, then the center of mass, or the average of their positions, will obviously be at the center of the beam. So instead of having our body look like 2 individual and separate point masses that are separated by some amount, then we can just look at our object as 1 point mass, where the mass is going to be the sum of the 2 individual masses, and the location will be at the center between them. Why is this useful? Because obviously now, instead of having 2 masses, we only have to deal with 1 mass. Now, in the picture, we've drawn the center of mass as a larger circle just to indicate that the mass is more massive than the 2 individual point masses at each end. But even though the circle that we've drawn is bigger, remember, we're still imagining this as a point particle, meaning it's still infinitely small. So now we can look at the beam as some massless rod where we have 1 mass located at the center. And this makes it much easier to answer how do we know if the beam falls over or not. We draw an imaginary line going through the edge. You can see we have this vertical dashed line above, and we have our little circle representing the center of mass. And basically, if this little circle passes our imaginary line, then the rod will tip over. If the center of mass is to the left of our line, then the rod will not flip over, and if it's to the right of the line, it will flip over. You can even think of this as just looking at a point mass, and obviously if the point mass is on the table, then it won't fall down because it's being supported by the table. And then if it's over the table, it will fall down. Think of those Looney Tunes where the Roadrunner runs over the cliff. As soon as he runs over the cliff, there's nothing holding him up, and he begins falling down. So now it's much easier to answer the original question of how far we can push the beam before it falls over. Let's assume that the right end of the beam was in line with the edge of the table. Then basically we can push the beam 1/2 of its length before our center of mass reaches the edge. So we can push the beam 1/2 of its length before it begins to fall over. Now let's look at a slightly more complicated object. Let's say that instead of this massless rod, which we assumed was just in 1 line, we have this rectangle. Again, we assume that the rectangle itself is massless, but we have now 4 point masses located at each corner. We assume that we know the length of the rectangle as well as the height, and again the question becomes, how far can we push this rectangle over the edge before it begins to fall over? Obviously, this shape, this system is more complicated than the previous one. First of all, now we have 4 point masses, and the actual configuration in space looks more complicated. But using the method of the center of mass, this is still easy to solve, especially when we're dealing with symmetric objects. By symmetric objects, we mean that first of all, the masses are the same, so the masses of each of these point masses are the same, and the relative distances are also symmetric, meaning that, for example, the distance between the bottom left and right point masses equals the distance between the top left and right point masses, and the distance between the 2 point masses on the left side equals the distance between the 2 point masses on the right side. So if we have a symmetric object like this one, then we know that the center of mass will be located at the center of the object, and the mass, the total mass, or the mass of the center of mass, will be the sum of the 4 individual masses. If each of the point masses at our corners had a mass of little m, then the center of mass, which again we're looking at as 1 point particle, that would have a mass of 4 times little m. And now it's the same as before. We draw an imaginary line through our edge, and we just ask, when does the center of mass pass this line? As long as it's to the left of the line, then the rectangle or our object does not tip over, but once it does pass this line, then it does tip over. And so the answer of how far we can push the rectangle before it falls over is also equal to 1/2 of the length of the rectangle. From this example, we see that the height doesn't actually affect our answer. The height is irrelevant for how far we can push our object before it falls over. Obviously, if we have a higher up object, then the center of mass will be higher up, but we really only need to measure the position of the center of mass along the x-axis to answer whether or not it will flip over. Now, an obvious question is, why does this happen, that the object only flips over once the center of mass passes the edge of the table? Let's draw a circle that's centered at the edge of the table. Now, let's assume that the center of mass begins to the left of the edge. And what happens if the object begins tipping over? Well, we can see that the center of mass happens to be aligned with our circle, and if our object begins tipping over at this point, then the center of mass has to escalate, it has to climb up the circle. But we know that things are much more likely to fall down than to just begin moving upwards. In terms of the height, that is, the center of mass would have to climb upwards for the object to tip over at this point. So now, let's move the object so that the center of mass is to the right of the edge. And again, let's look at what happens when we draw the circle. At this point, once the object begins tipping over, then the center of mass, following the circle, begins moving downwards. In other words, it becomes lower in height. And so if we just look at the height of the center of mass, then this helps also explain when the object will tip over. Anyway, I hope this helps explain what the center of mass means and how it can be useful. It's obviously much easier to work with problems involving one object, one mass, as opposed to, say, 2 or 4 or more objects. And this is something that will come up time and time again. With all of that said, let's move on to the next video.